My name is John Pavich. I'm leading the HPC efforts at Convergent Science as lead of the HPC team. Much of the core framework has been completely redesigned in CONVERGE 3.0.
My name is Cooper Burns, and I'm a research engineer at Convergent Science in the HPC team. With these changes, we are seeing a significant improvement in scaling.
My name is Keith Richards. I'm co-owner and vice president of Convergent Science. I work very closely with the development team still at this point in my career. So I've been heavily involved in the 3.0 development. And we first started talking about 3.0, I guess it was about 5 years ago. We were early on in the 2.0 version development, and we could already see that there were some limitations coming up in the code that at some point were going to have to be addressed. Some of those were going to involve more of a code change than we were just doing in our incremental 2.x version changes. When we wanted to say that particular feature is something we need to address, but it won't happen right now, we used to just say 3.0. That was sort of our friendly way of internally saying we'll deal with it later, but it is going to require a major enhancement. Those limitations that we had in the 2.x 5 years ago still weren't a major issue for our customers. Most of our customers had adequate speed and were able to run on as many cores as they wanted. However, after a couple of years, some of those limitations that we were going to address later started to become real limitations for our clients that they were addressing. So instead of using the term 3.0 to say, hey, we'll deal with that later, we would just say 3.0 as a way of saying, let's get on this now. It was sort of a call to action. So at that point, about 3 years ago, there were only a few of us that would meet regularly to talk about design features and some of the basic structure that we were going to have in 3.0. Eventually, that grew to incorporate the entire HPC team, which was composed primarily of computer scientists.
All designs have a shelf life. Design requirements are always shifting on you as new features are requested and as current features need to be enhanced. Even with the best designs, you end up having to eventually rethink your core structures that you've set up. Symptoms of an aging design. One of the first you run into is performance issues. Every time you come out with a new release, it's getting slower. Instability problems. As new devs try to implement new features, they run into old hacks that they didn't understand the context of. Compatibility problems. Each new release, the dev team is struggling with trying to stay compatible with previous releases. Finally, you'll run into development timelines just keep getting pushed back. The Converge development team has officially adopted C++ instead of C as the language of choice driving future efforts. Embracing C++ allows us to leverage both the performance aspects of a low-level language along with the cross-platform benefits that C has offered us in the past. However, C++ also allows Converge to leverage modern software designs that can really only be utilized through a modern high-level language like C++. Much of the core framework has been completely redesigned in CONVERGE 3.0. There is no case that isn't significantly impacted by it. This includes core back-end mechanisms like our new Mesh API, our surface and grid manipulation tools, our input and output file formats, and our load balancing algorithms. The main benefit of the code restructuring is, in short, an improved user experience. Hardware paradigms are changing, the complexity of CFD problems are evolving, assumptions that could be made 10 years ago are no longer valid. The paradigm has shifted. Modern hardware developments have put more stress on the software developers to better utilize the hardware. This will also result in user interface improvements, and as time goes on, Converge will start to feel more like a flexible toolbox, which you can use to solve any CFD problem.
was about 2 years ago that 3.0 was sufficiently written that we could expand development to include the entire development staff at Convergent Science. At that point, we got everyone involved in porting their particular features over to 3.0 and building on that code base that had been written by the HPC team.
Many of our users use CONVERGE to simulate combustion. Reacting flow CFD requires fast and accurate chemical mechanisms for dependable predictions. Over the years, we have been adding to our chemistry toolbox in order to provide our users state-of-the-art utilities for creating, reducing, or optimizing chemical mechanisms. With the new feature in CONVERGE 3.0, we provide more reaction mechanisms tools than ever to complement our fast and accurate CFD. We have added many new chemistry tools and improved upon existing chemistry tools in CONVERGE 3.0. Our new features include 0D reactor models, such as variable volume with heat loss, the well-stir reactor, the homogeneous charge compression ignition engine, and the plug flow reactor, as well as a new 1D model, the freely propagating premix flame. We also have new table generation tools, which are tabulated kinetics of ignition, TKI, and tabulated laminar flame speed, TLF. These improvements will help users make better choices when selecting mechanisms for 3D simulation.
In 3.0, the CONVERGE solver will couple with the Abacus FEA solver and also a variety of spatial products. Coupling with Abacus FEA software will enable users to perform a wide variety of coupled fluid structure interaction problems. Abacus uses finite element analysis, which is a class of numerical methods which are used to solve partial differential equations in the engineering domain. It is the method of choice to solve for structural deformations and solid dynamics problems. The coupling with Abacus is facilitated via the post-simulation engine API, which is provided by Dassault Systems, which is the parent company of Abacus. Through this API, CONVERGE will communicate the fluid forces at the fluid structure interface to Abacus, and Abacus will use this information and calculate the solid deformation and pass this information back into CONVERGE. While CONVERGE has its own inbuilt FSI module, coupling with Abacus will enable users to leverage Abacus's much more extensive FEA models to perform much more complex FSI simulations of engineering interest in multiple domains. Coupling with Spatial will enable users to import CAD geometry directly into CONVERGE Studio and perform the triangulation on the fly. It is also much more difficult to correct the errors in a triangulated surface without knowing the intended geometry. Thus, in CONVERGE Studio 3.0, we will use Spatial's 3D inter and 3D precise mesh to perform the triangulation.
Periodic boundaries can be a powerful tool for reducing the overall runtime of a simulation. In CONVERGE 3.0, we added the capability of matching one cell on one side to multiple cells on the other side. This way, there are no restrictions on how the geometry should be oriented anymore. And users can also have a curved periodic boundary. They can set up multiple pairs of periodic cases with different types, and it's easier to set up cases with complicated geometries.
So two of the major driving factors for the 3.0 rewrite were the modularity of the code and scalability of the code. Besides this, there's an additional feature that was put in called Inlaid grids. Now this didn't necessitate a code-based rewrite, but the timing was right to put it in anyway.
Inlaid grids are grids that can be generated by the user in Converge Studio. These would be used to typically resolve portions of the domain where using a Cartesian grid can either be inaccurate or expensive. A common example of this would be the boundary layer region of the wall, where using a Cartesian grid can get quite expensive. This is because cell embedding for the Cartesian mesh happens in all three directions. Now the user has the option to create an inlaid mesh, which would have a fine resolution only along the wall normal direction, as opposed to the resolutions along the wall parallel directions, which can be much coarser. Converge would then use the inlaid grid to resolve the boundary layer, and then use the Cartesian grid to resolve the rest of the domain. Like other boundaries in Converge, inlaid grids are made of triangles. And these triangles are grouped into a separate boundary, which the user would have to specify. So once this is done, Converge then knows to figure out the rest of the properties of the inlaid mesh, such as the number of cells, their shape, location, etc. For the remainder of the domain, which is not covered with inlaid grids, Converge uses the regular Cartesian mesh. Inlaid grids allow the user to run Converge with a grid of their choice. Let's say if they wanted to have a mesh which was aligned with the flow. Now the user has a choice to create an inlaid grid which can be oriented in any direction and can be aligned with the flow as they like. So the user has a freedom to create inlaid grids for some walls, as opposed to having to create inlaid grids for all wall boundaries. So for walls of interest, the user would create an inlaid grid. And for other walls, they can just use Converge's wall modeling approach.
Scaling in Converge 2.x was limited in two main ways. First, the parallel block structure severely limited our ability to evenly distribute work among processes, especially in cases with highly varying embed scales. Second, we required each process to have a coarse view of the entire computational domain. This meant that at high core counts, our memory requirements became untenable. For Converge 3.0, we have completely rewritten the parallel mesh data structures in order to allow for an arbitrary partitioning of cells. This allows us to have a good work distribution, regardless as to the number of embed scales, AMR levels, base grid, etc. Additionally, we have removed the requirement that each process has a coarse view of the entire computational domain. This allows our memory scaling to match our compute scaling. This will help users whose cases are memory limited. The major difference is that load balance is now done directly on the mesh instead of on the parallel block structure. Additionally, we allow for automatic load balance detection, which means that the case is well balanced for as much of the run as possible. With these changes, we are seeing a significant improvement in scaling. Our previous recommendation was 50,000 cells per core, but in Converge 3.0, we are recommending as low as 3,000 cells per core, assuming that you are running on InfiniBand. Users will now also be able to run many different embed scales, as well as larger levels of adaptive mesh refinement, allowing them to capture more flow features without adding cells where they aren't needed. Additionally, users will be able to take advantage of large core counts in order to reduce the per core memory requirements.
Memory savings in 3.0 are mainly attributed to three different strategies. We have targeted three main parts of the code, namely the solver, the surface, and the mesh. In previous versions of Converge, certain information was stored redundantly. This used extra memory and required frequent copying of the data, which affected the runtime. We have removed these redundancies and streamlined the storage by utilizing new and better data structures. For most cases, this reduces the memory and reduces the runtime as well. For the second strategy, we have changed how the surface triangulation is stored. Previously, every core or rank stored an entire copy of the surface triangulation. For cases with very large surface files, this became a limitation. Very little memory was left for the solver and the mesh, because most of it was consumed by the surface file. Now we are taking advantage of a new feature in MPI called shared memory. This allows all the ranks or cores to store and share a single copy of the surface triangulation. Our third strategy involves the mesh. In previous versions of Converge, every rank stored an entire copy of the octet tree down to the parallel block size. The limitation was that as the number of cores was increased, so did the memory, hence it did not scale well. We rewrote the mesh code such that we do not have this limitation. Now, every rank only stores the mesh or the cells it needs and nothing at a global scale. Our users can increase the number of cores for a simulation and expect memory per core to be less.
User-defined functions, or UDFs, are one of the most important features in Converge. They enable our users to use our robust meshing framework to solve the really hard problems. The problems that we haven't thought of yet, that require specialized models not yet supported in Converge. UDFs also give our research and business partners a platform to develop without access to the entirety of the Converge framework. This is good for them, this is good for us, and ultimately it's good for our customers. The v3.x UDFs will operate more like a true plugin interface rather than single-use functions tailored to a simulation. The new framework allows users to write more portable UDFs across operating systems and backwards compatible UDFs across minor and in some cases major versions of Converge. The new API focuses on allowing users to write UDFs more easily without having extensive knowledge of the internal workings of Converge.
With this new version of our software comes a new installation package. The 2.4 package was extremely minimal and really only included executables, while the 3.0 package includes MPI as well as all of the other dependencies we require, and scripts that will help our users to set up their environments at runtime. This new installation package provides our users with a number of benefits. One, users no longer have to install MPI or any other dependencies themselves, though they still can if they want. All of our dependencies are installed by us. Two, users no longer have to copy our executables around, as the install package includes a number of scripts that should help our users to run our solvers, MPI, and utilities right out of the box.
These are the improvements that we are so proud of in Converge 3.0.